and it's got some stuff in there. I was like, where did they get this question? I mean, it's like some of you have done it, this mutual inductance thing. That stuff's really hard. I mean, that's like beyond the pale. But luckily, it's all in the hints part. So if you use the hints, you can kind of, like I did, slug your way through it and go, oh, okay, thanks for the hints. Because I was like, oh my, I know how to do this one way, but that's way beyond the scope of the course. And I don't ever remember saying the words mutual inductance to you all. And then all of a sudden, the second question is mutual inductance. And I'm like, oh no, I can't believe. Basically what mutual inductance is if I have a coil over here going bunk, 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 like this, changing current. In other words, the current's going up and back like this, then that means that the magnetic field is changing. So a coil over here is going to what? Experience a changing magnetic field. So it'll mutually induct the thing here. That's what that was all about. So that was kind of screwy. And plus, on their very first question, well, shoot, let me just go to it and show you. So we can just talk about it real quick and you can kind of get started. Plus, on the very first question, they say, give a numerical answer, and it's an algebraic answer. I was going nuts. I was going, I can't get, you haven't given me anything to give you a numerical answer except for the permittivity of free space, or permeability of free space. And there's other things in there besides that. And they said, whatever, it's an algebraic answer. And I went, oh my, that doesn't do me any good. So, anyway, all right. So let's take a look at it real quick, because I actually believe, I'll do some of the problems on Friday, but I actually think that, I'm sorry, I've got to go through all this loading and unloading here. Okay. All right, courses. Of courses, this is you all. And let's go to chapter 21. I haven't looked at chapter 22, but a resistor in an RLC circuit. This one's not bad. This one's okay. This one, you just got to kind of mess with it a little bit. But if you, like I said, if you use the hints, you'll come out, it'll be all right, okay? Yeah, that one wasn't bad. But this next one, determining inductance and shoot. Give you the answers right away. On some of these, too slow. All right, but anyway, on some of these, when it says express your answers in terms of V naught and I naught, that's fine. I can do that. Okay. And the EMF V naught and frequency F and the current. So XL, this would just be your, they just want you to do Ohm's Law here. Remember, XL and XC, this is the inductive reactance, and then there's the capacitive reactance, all right? And that reactance part, that R part, the way I remember it, okay, that tells me it's a resistance, so it's in ohms, okay? So this is just an ohm here when you get this ohm. And so what's Ohm's law say? V equals what? IR. Okay, point. Right. So if XL, since it's the only resistor there, okay, and we're going to keep that, if we keep that frequency constant, well, the AC voltage is changing, but we'll just express it when it's at a maximum. It's just V naught over I naught is all that comes out to be. And then what is the inductance? And then you express it in terms of F. You got to put your 2 pi in there. Remember that 2 pi times the frequency equals times the inductance. The inductor gives you the inductive reactance. And then what would happen to the amplitude in the inductor if L were doubled? And I believe it would be halved. Let's at least go to there. Because you'd be dividing it, so you'd be dividing a double. So if I divide a 2, that's halving it. Ta-da! At least you got that part right. through part B, this right here? Well, L is equal to 2 pi f times, the inductance then, here's what they want you to do. What is the inductance of the inductor in terms of V naught, I naught, and F? Well, if you know that XL is equal to V naught over I, here, let's just do it. I'll just show you real quick. It's not that tricky once we get to it. Where's my papers? All right. Here we go. All right. Now then, we'll zoom in a little bit. Zoom in. Okay. If we know this, if we know that XL equals V naught over I naught, okay, and I know that XL equals 2 pi F times L, well, what do you think L is? How do we get L? We take this and stick it in there for that, and then do a little division, and I think you got it. So V naught, so L would equal V naught over 2 pi times the frequency times I naught. And the most annoying thing is just having to type all that in. Until you get to the next problem, which is, I guess I didn't want to go through this, but I was so rattled by it by going by the assignment. Next time I'll check it first. Yes? Yeah, you put a 0. Oh, okay. Jordan's question is this. When you do this, when you do those subscripts, that's for a laptop. We don't have a laptop here. Yeah, when they ask, you put a 0. Don't put an O, because it'll say, this answer doesn't have variables in terms of O. And you'll be like, oh, I didn't mean, put a 0. Breathe and put a 0 down. It's kind of like when they give you the different orientation off a thing. You know, it's the sign. Okay. They'll do that to you sometimes because they don't think this stuff's hard enough as it is. All right? Okay. All right, now then. So that was not bad. Then I'm going to have nightmares over this one. All right? Oh, answer, oh no, I'm spilling the beans here. Answer requested, because I was just like, numerically, I can't do it. I can't do this numerically. So I went, well, what the heck? Well, show it to me, bastards. And so they did. I mean, I knew how to do it. Now, wait a minute. Now, what do they show it? All right, take off into and this A here. Try and remove those guys. All right. And what is that? What do you have the formula of that right there? This right here would be the, that's the magnetic. Yeah. All right. Go ahead. Right. Because I didn't say anything about mutual inductance and how to find it. Yes, Kim. You can't read that? Good. You'll have to do it then. No. No. It's equal to mu naught. Okay. Your little permeability of free space. Okay. Times N1, which is the number of turns in the first cylinder, times N2, times the area of the thing divided by L. Okay? And see, it's a funny thing because look at this. Look what you have here. You've got, hold it down real quick. Look what you got here. You have area divided by L, which will give you meters, and you've got turns, just numbers. Then you got your good old permeability of free space, which tells us what the thing is. Okay? Was that the only question on that one? Yeah, it had a bunch of hints. Go through the hints, and you can see it works it out for you if you go through the hints. It really does. Oh, Derek, you didn't have a question. You already saddled up here and got the answer, didn't you? All right. Well, what if they change the variables? They won't. They won't. All right, so that, yeah, I spent like 10 minutes on that going, goodness gracious, what are you doing? Oh, no. Okay, all right. Now then, Okay, well, shoot, let's just look at these then, I guess, since we're here. Might as well look at them. Now, all right, on this one, in other words, I kind of like this because this is okay. This is an okay thing. Yeah, hold it down here a little bit. I've got you all wound up now. But anyway, this is kind of a good way to show, here's the way the voltage is going through a circuit. Okay, so you got the voltage, and this is going up, and I almost had to come in here and put it on the big screen so I could read it. I couldn't read it even with my glasses and everything because it's so faint. But this actually goes up to 170. Okay, so the VRMS, so if the max voltage is 170, how do we find the VRMS, the root mean squared? What do we do? Ooh, don't multiply. Think about it. That's what I did first. That's not right. You don't multiply it. You divide because you want the smaller number. Yeah, she kind of knew it right when she said it. But anyway, because if you multiply it, you're going to get like 210 or something like that. All right, so, and we pretty much know that what's coming out of here is bouncing between 170 and negative 170, the polarity. And so the root mean square of it going right across here and going right across here is about 120. Okay? And so then, what do they say? Oh, part B. Let's hit the thing for part B. Can you actually do math on here? Yeah. You can? Yeah, you can just type it. So you can go like 170 divided by square root of 2. Watch this. Yeah, I didn't know you could do that. All right. Too fetty. Good. All right, now, move on. All right. Okay. Now then, it says when a lamp is connected to a wall plug, okay, here the lamps, okay, so the only resistance we have then is, oh, press B, thank you. I'm getting prompted here. Press B. Okay, this is the only circuit we have. Got a little AC going. Got this thing, 120 amps. 120 amps? What am I talking about? How about 120 ohms? Okay, and so the IRMS would be what? What's the voltage here? Or the amp? Gosh, dang, I'll get it straight. What would be the amperage if V equals IR? What's the amperage? I can do this one in my head. Yes, 1. Exactly. Exactly. And these guys don't change their answers, I don't think. So if you're following along closely. All right, now, what's the average power dissipated in the thing? Average power, remember, is this VRMS times IRMS, VI. IV, whatever, same thing, IV, VI. Okay, but now, you could also use the peak. In other words, you could use the peak, you could use 170 times the square root of 2 and divide that by 2, and you should get the right answer too. But don't worry about it. I just got some rolled eyes like, what did he just say? Basically what I was doing was, remember, the average power is peak power divided by 2. And so the peak power would be when it's at V naught and I naught. And here, in this case, I naught would be this times the square root of 2. So the peak power would be 170 times the square root of 2 divided by 2. And then you'd get the right answer. I'm going to try it. I'm going to play with it to see. I mean, because we all know that, oh, we can just multiply by, we should get 120. But I'm going to see if 170, I'm going to try it. I'm going to play with them here. See if 170 times the square root of 2. What? Oh, I was doing it on my calculator. Yep, I get 120. I got 120 that way. If you do 170 times the square root of 2 divided by 2, you get the exact same answer. You get 120. Yeah, you should. Yeah. Okay. All right, what else? What other tortures do they have here? What? I skipped one. Well, you're going to have to do one. I mean, all right. Oh, shoot. I did it again. All right. Now then. Oh, it changed the numbers, though. Ha, ha. It's slick. Okay. All right. Now then. An LRC circuit has an inductance of 0.420 henries, a capacitance of 2.65 times 10 to the negative fifth farads, okay, and a resistance of R. Ooh, is this the one that was driving me nuts too? What's the angular frequency when R is 0? Okay, we're just going to let R equal 0. Okay, we're just going to say that the R is 0. Okay, and so we want to basically what we're going to do is we're going to set these two guys equal to each other. Now here's what you do. Oh my, yeah, use your hints on this guy. All right, I'll do the first part, and then you guys use your hints on the second part. Now, well, let's just do the hints because they explain it better than I would anyway. So we come up here, go to the hints, boom. It says the angular frequency of an LC circuit. Okay. Angular frequency is equal to this. Aha! Well, then I think I can do that. Then, and the reason they're doing that is because when it's at 0, this is basically when there's no resistance. Then recall that an angular frequency of an LC circuit with no resistance is given by this: omega equals 1 divided by the square root of L. Or there you go. They gave you the formula right there. Boom, and you can go in and plug it in. And remember, what happens if we take the frequency, 2 pi times the frequency of this is also equal to, if we divide, we can find the resonant frequency, F naught, if we take this and put a 2 pi right here. Put a 2 pi right there. Then you get the resonant frequency. In other words, those two are in sync that way. It gives you the resonant frequency. All right. So that's not too bad. So the hint actually kind of walked you right into it. And then this one, all right, now this, look at this. I was struggling. I went, all right, I'll use a hint. I'm not proud. So I always went, okay. All right, it said calculate the angular frequency of the circuit. Well, we used the 1 over the square root of LC. Okay, boom, got that. Now, to find when it is 8% lower, what would you multiply that by to find an 8% reduction? 0.08 or 0.92? If you multiply it by 0.08, you're fine as long as you subtract that from 1. But you can multiply it by 0.92. So you get your old answer, multiply it by 0.92, and then you go, okay, I got that. And then look at this bad bear. I almost chuckled out loud. There we go. And then they say, oh, okay. Then it's real simple. All you got to do is this. I went, oh, wow. How did they do that? I don't know. I'll have to go back and look at it. I mean, this guy looks familiar. I think it has something to do with, oh, I know what they're trying, yeah. But don't worry about it. I just went, fine. I'm glad it had hints. Then you're on your way. Okay. Now remember, your numbers may vary to protect the innocent. All right? All right. Problem 6. Difficulty 1. Now this wasn't so bad. Oh my goodness. Yeah, they're going to change the numbers on you. All right, so here we go. It says, no, it didn't. Oh, well. All right. It says operating at 60 hertz has an inductor with an inductance of 1.53 times 10 to the negative 3 henries, a capacitance, and a resistance of this. What is the inductive reactance of this circuit? Basically, they want you to find XL, okay? That's the first thing they want you to find. That's easy. XL equals 2 pi F times this guy, the henries. And then they go on and they say, all right, Now then, they want you to find XC, I believe. They want you to find XC, which is okay. Now remember how, this is the way I do, this is the way I find XC, is I can just go ahead and type in 2 pi times the frequency times the capacitance, and then flip it over. Hit the x to the minus 1 key, the magic key, and it flips it over, and we're in good shape. And so then, and then when they want the total impedance, which I think you had to do for your lab, right? The total impedance becomes Z equals, and that's that square root of R squared plus, now inside the square root, you do XL minus XC, close the parentheses, and square that. Okay? Because remember, you had the two phasor things over here. XL was going up, XC was going down. So you subtract those two to get that impedance going through there. And then that's not too bad. This is a nice review of impedance in IRMS. Okay, 120 volt AC outlet. Is that VRMS or is that V naught that they're giving you? That's VRMS, okay? And when you're taking your test, this is what your test question for this chapter is going to look like. I'll just tell you right now. It's going to look like this. You know, find XL, find X. It's not going to be find mutual inductance, anything like that, okay? Mutual inductance or anything like that. But it's basically going to be, hey, here's the frequency, here's the VRMS. You know, here's the henries, here's the farads. Just basically find the impedance, find the IRMS, find the power. It's going through there. Okay? Find the phase angle. Okay, now I think they do us dirty here on one of these. No, F naught. Oh, okay. Okay, now then. Oh, here they give you the formula for finding F naught, so that's a piece of cake, which is your resonant frequency. And I think, Richard, what was your question? You sent me an email, and I was away for the weekend, and I didn't have a computer nearby, and I was just kind of reading my iPhone and went, oh, I don't know. But what was your question? What was it on this one or the previous one? Okay. All right, you can just come see me after then. See me after. Oh, answer requested. He did it again. You know what I kept doing? I kept forgetting to take the square root on this thing. So this might have been it. This might have been it because you were saying, wait a minute. What's the angular frequency of the circuit? Now, the angular frequency of the circuit is equal to F naught. All right? So, well, is equal to 2 pi times F naught. All right? And so here we go. It says an LRC circuit, the resistance is, now if we go to the hints, let me just redo it so you can see how it's done. Oh my, is it 2:27 already? Yep. Goodness gracious, we're not going to learn about light today. All right, we might. Light's pretty cool though. I mean, it'll be straightforward. I could teach you that chapter in 10 minutes. That's what I thought about this one too. But this was hard. I forgot. I was like, oh yeah, unless you do this all the time, this chapter is kind of tricky. All right. Relationship between current and voltage amplitudes, there they go. We can generate the highest amplitude at I max, all that kind of stuff. All right. And I max equals V max divided by Z, which would be your total resistance. Okay. It's the expression for impedance. Okay, first of all, they want us to find which one of these looks like the expression for impedance. This one? Any votes? Votes for this one? Some of you on the side can't see it all. What about this one? Ooh, I heard a yes. All right. The rest of you going, would you please just go on with it so we can get this done? All right. This one? Nope. And this one? Nope. It's this one. I do believe. So there we go. Get that out of the way. Now we come down here. Finding the formula for the resonant frequency is this. In other words, now, you take this formula here, and boy, Okay, here's the thing. Those of us in physics, sometimes we bandy about the word frequency, and it can drive someone crazy who's not tuned in to what we're doing. All right, because you're going, wait a minute, that looks like a radians per second to me, not a frequency. Yeah, that's true. But all I got to do to get my frequency, to actually get my frequency, is just divide this guy by 2 pi. Okay, because 2 pi equals 2 pi times the frequency equals the radians. Okay, the radiant speed of it. All right. All right. So anyway, you just set your L omega equals 1 over C omega, and you go about solving it, and then you'll get 1 over the square root of C, LC. Now, so if you take L times C and take the square root of it, and then hit your x to the minus 1, you should be good. I kept forgetting to take the square root of it. Kept getting the wrong answer. Okay. All right. So that's not bad. Did I do this one too? No, because this is just multiple choice. You can use hints and take a guess. True, false. Well, remember, it's probably never ever this one. It's probably never ever cannot be determined from the given information. All right. Single inductor is connected to an AC. Okay, so we got when the current in the inductor is at a maximum. Okay, so when the current's at a maximum, the voltage across the inductor is not changing. Is the statement true or false, or cannot be determined? Okay. All right, what's happening when the current in the inductor is not changing? I think that's false. Because this is all about changing AC circuits. Yeah. Anytime you're dealing with AC circuits that says voltage isn't changing, that's wrong. Because that's what this whole thing's about, is changing voltage. All right. Okay. There you go. All right. Then I think I stopped here. Whoops. Time out. Stop that. There we go. All right. Okay, here's another thing. It would look like a test question. Question 10 looks pretty good. Except when you get down here, when you get down to this guy, it says, what's the phase angle between the current and the applied voltage? And I think we learned that the phase angle looks like this. Hold on a second. Let me go to the dot cam. We said that the tangent of the phase angle is equal to XL minus XC over R, right? Isn't that what we said? Now, what happens if you don't have an R? What's that angle? If R is 0, what does that right side go to? It's undefined. Exactly. So what tangent angle is undefined? The tangent of this certain angle is undefined. Which is it? What? You all can figure it out. Plug it into your calculator. Eventually you'll get it. 90 degrees. Okay, remember, the tangent of an angle is y over x. So if x is 0, where are you on that unit circle? What angle are you at? Right, 90. Okay, so that one, I was like, well, wait a minute. You didn't give me a resistance. How can I? Oh, sorry, it's 90. Okay, now. So, and I think I don't want to do any more because that's where I stopped. No, I didn't. Okay, that one was kind of fun. I could. Okay. All right. And then once you get through these guys, now it just becomes straight, good old type problems, RLC circuit type problems. This says at what frequency should the circuit be driven for the maximum power to be transferred from the something to something? I don't know. Let's figure out what it says there. Hold on. 75, 100. There we go. Transferred from the driving source. Okay. All right. Maximum power is going to occur. All right. Maximum power is going to occur at the resonant frequency. Okay. Maximum power will occur at the resonant frequency. All right, why is that? Because that is where your XL minus your XC, your reactive inductance, or your inductive reactance and your capacitive reactance are all cancel each other out. Okay? So that's what they want you to find. They want you to find the resonant frequency. And says, what is the impedance at that frequency? Oh, well, that's not bad. Did they give us a resistance here? I bet you if you plug in, I'm just gonna try it. If this is wrong, I'm going out on a limb here. I'm gonna say it's 55 right here, and let's see what happens. Hopefully that's right. Why do I think it's 55? Because the resistance R is 55, and if I take XL minus XC and they 0. It should work. It should work. Please work. Yes! All right, good. So what I told you is correct. All right. All right, and I'm afraid to venture on to 13 and 14 because I got away with one here. Remember what I told you about doing physics on the fly. I hadn't seen this problem yet and was just kind of going, All right, you should never do physics on the fly. You should probably never take up a whole class period doing the homework problems either, but that's okay. Wanted you to get a good start. So we did 12 of the 14. Let's just see what the next, I'm curious now. Oh, the power factor of the circuit. The power factor of the circuit, there's an equation, and I forgot what it was. So you can figure it out. It's in the book. It's in the book with the, I think, I know what it is. Here's what you do. You find that phase angle. Remember what the phase angle formula was? XL minus XC divided by R. Looks like they gave us capacity. Here's XL. Here's XC divided by R. You find that, take the inverse tangent of that, find the angle, and then take the cosine of that angle. And that should work. Okay? That should, they give a different thing in there. And then if the circuit operates at 6 units, what additional capacitance should be connected to give power factor of unity? Oh, okay, so I think what they're asking there, we got to find the new, got to add a capacitor to that thing so that my XL minus my XC is equal to R. That would work. Yeah. Because then if you get XL minus XC equal to R, you get 1 divided by 1, so you get unity. That's what they're talking about. So that has a power factor of unity. Oh! No, power factor of unity means my angle needs to be what? 0. Yeah, so that would work. So in other words, yeah, you want the new capacitance to equal the, you want to add capacitance to it so that it equals 510. 350 plus what? Plus 350 plus what is equal to 510? Well, it's 160. So you take that 160, then equals 1 over 2 pi frequency times C, and you take it from there. I think that'll work. Seems like it. Seems like it should. Yeah. Good. I need verification for the back. Thank you. All right. And then we'll take a look at Ford. All right. Shoot, we're already there. The suspense is killing me. What's this one look like? Oh, good. This is straight, good old. This is just a good old straightforward. With an inductance is tuned to an FM station at 930 megahertz, 90.3. Oh, it's almost close to my favorite station, 90.1 KKFI. But anyway, do y'all ever listen to that? It is the best radio station in the city, no doubt about it. Every once in a while it gets a little fun. I mean, they kind of go off on the deep end, but that's okay. 90.1 KKFI. It's just right there at 39th and Troost. That's where they broadcast from. It's free radio. I mean, it's called community radio. In other words, the DJs are not really trained either. And so it's kind of funny. Sometimes they're like, whoops, couldn't get that song to queue up. Let's try this one. And they also play a lot of local artists, a lot of blues, a lot of just, you name it, they play it. All right, anyway, so this is just a good old straight RLC circuit. We got our Henrys here. We've got our frequency here. And so we're going to figure out what our XL is. What's the capacitive reactance? Okay, the capacitive reactance, XC has to equal XL for this one, for this radio to work. Okay? All right? So, by adjusting a variable capacitor, so I've got the Henry, so you'll find XL, and again, it says XL minus XC equals 0. So if XC equals XL, then you're on your way. All right? And then, so you can get your ohms here, and then you work it backwards to find your capacitance, and you're good. All right. Well, once you get through the first 4 problems, the homework assignment kind of goes downhill. But I was a little. All right. Now stay put for 3 minutes. I'm going to show you real quick. We're going to look at real fast, and this is kind of cool stuff. We're going to look at light. All right. All right. Now then, here we go. Now, we finally start. I promised you, I kept promising you, after 2 tests and thousands of lives, it starts to get easier. This course starts to get a lot easier. All right, this is we've got a cool demo like this too, where it's where we actually shoot some water out. It shows the total internal reflection or refraction of the light. It stays inside the water. You got this green beam that kind of bends around. Okay, but anyway, all right. Basically, what we've got is this. We're going to look at wavefronts. Basically, we're going to be out here because the light source is going to be, for optics reasons, where we're dealing with wavelengths of nanometers. If you're dealing with something times 10 to the negative 9, and you're 2 meters away from it, that's pretty much infinity, all right? As far as that wavelength is concerned, that's pretty far away, all right? Because you're 10 to the negative, you're a factor of 10 to the 9th away, which is 1 billion times away. So that's almost. So we pretty much deal with these nice planar wavefronts, okay? And the eyeball works with that way too. So we got these wavefronts coming out, all right? And how fast are they traveling through a vacuum? These electromagnetic light waves, how fast is light traveling? Speed of light in a vacuum. Now, when it hits glass, or when it hits water, or when it hits you, it reflects back slower, all right? And it also refracts, okay? Like one of my questions that I used to ask for extra credit, but I don't anymore, was this. Why does light pass through a glass, but it won't pass through this wall? What's the difference? There's a lot of reasons for it. Yeah, the wall completely reflects it too. Yeah, it absorbs it. Because 3 things happen. It either absorbs, refracts, or reflects, or a combination, or so that'd be 4 things. Or a combination. There's 3 kinds of people in this world. Those who can count, those who can't. But anyway, there's 4. Okay. All right. 4 things are a combination of those. Okay. All right. So anyway, here's the big equation. Then we'll stop. Right here is where we'll stop. It's reflection. Okay? Now, what you have to get used to is, and I did a bad job. The book did a good job in chapter 20 of explaining that we're measuring the angle off the normal for the magnetic field. And so some of you, when it said the magnetic field is coming perpendicular out of the surface, you thought, oh, well, then it's 0. No, because that's where we measure that angle off of. Okay? We measure the cosine of the angle off of that. Same thing here. We are taking it, we're measuring the angle off the normal. All right, so we measure the angle off the normal. All right, and for a nice flat piece of mirror, nice flat piece of glass, very flat surface, the angle of incidence equals the angle of reflection. And we'll stop there. That's where we'll pick it up, and we'll finish this chapter on Friday. Well, now we do have class on Wednesday.